talking about what more can we learn from protected local operators.
Okay, thanks, Sarah, and thanks, Alessandro and Giulio, for the invitation to this workshop. Yeah, so I'm going to talk about what more we can learn from protected local operators. And for this talk, I'm going to be sort of closed-minded and insist that the operators that we study are sort of well-defined bulk operators that are not attached to any defects or anything exotic like that. So nowadays, maybe that seems a bit more like, writing a book without using the letter E, but we'll see where we can get nonetheless. So this is in collaboration with many people, in particular with Anindya Banerjee, who's a postdoc at Queen Mary, Chinmaya Bhargava, who's one of my PhD students there, Hongyang Jiang, who's a postdoc at Queen Mary, soon to be at Imperial next year, and my longtime collaborator, Takahiro Nishinaka from Osaka City University. And also there's some stuff in progress with various of these people, and also Andrea Manenti, who's currently in Uppsala and I think moving to Paris in the fall. So this is the list of papers that I'll touch on. The first part of the talk is going to be actually more experimental with just some conjectures. So if you have input or complaints, please let me know. So let me just give some kind of brief introduction. So for concreteness, I'm mostly going to discuss protected operators in the context of 4D n equals 2 SQFT and SCFT. This is because there's a lot of fun math and physics, at least that I personally like, that's involved. But of course, a lot of the stuff that I'm going to discuss will apply more generally. So protected operator for me will mean some operator that sits in a short multiple of supersymmetry. So some multiple that satisfies some shortening conditions with respect to the supersymmetry algebra of 4D n equals 2. So these kinds of operators, of course, I don't think I need to tell anybody, are extremely well studied. For example, when you start the bootstrap process, the superconformal bootstrap, the first 4-point functions that you try to study are operators that involve various short multiplets of supersymmetry. So famously, people have cornered, various low-rank 2,0 theories using, say, the 4-point function of the energy momentum tensor, and other theories have been studied as well. You learn new things about n equals 4 super Yang-Mills. You can study various kinds of protected 4-point functions, and the point is that, of course, studying the bootstrap lets you take these protected operators and learn things about more general, non-protected operators. So one of the things I'd like to discuss are some ideas for trying to look at the non-protected spectrum using ideas other than the bootstrap, although I will only sort of kind of unfortunately vaguely hint about those things towards the end of the talk. But let me just sort of stick with the bootstrap for the time being and just mention that, studying these 4-point functions also leads to interesting physics by studying different OPE channels. So famously, in the context of n equals 4 super Yang-Mills, being Rostellian collaborators looked and saw various interesting meromorphic contributions to these correlators, and then found these new kinds of twistings that you could do to n equals 2 theories, and found new relations with chiral algebras. So studying these kinds of objects are obviously very, very interesting and profitable, and sort of perhaps more closely related to this workshop. I think, as everybody knows here, the relevant deformations of superconformal field theories, at least 4D n equals 2 ones, are given by various protected operators. So you can deform the prepotential by some chiral operator with dimension less than 2, or you can deform the theory by some mass term, and you initiate some renormalization group flow to the infrared. Also, as we saw in Cyril's talk this morning, and also in Michele's talk, you can also study moduli spaces. So where you give expectation values, say to chiral operators or to Higgs branch operators, and you can study the corresponding moduli space of vacua. So for example, when you give an expectation value to a chiral operator, you go onto the Coulomb branch. When you give an expectation value to some kind of Higgs branch operator, so here I have in mind a moment now, but it might be something more complicated. When you give an expectation value to such an operator, you flow onto the Higgs branch, and when you give an expectation value to both of these things, you flow onto some kind of mixed branch. So these operators, these short multiplets, these protected operators that live in these short multiplets, obviously control a lot of the UV physics. At the same time, as we saw from Cyril's talk, the infrared theory also has protected operators. I mean, they have free fields, and these are in fact more protected generally than the operators in the UV. And the reason is that not only do they satisfy the usual shortening conditions that you have away from unitarity bounds in interacting theories, but you also have various free equations of motion, so you satisfy even more protected shortening conditions. So some of the operators that appear in the infrared are maybe better thought of as operators living at the end of defects, like the hypermultiplets, these hypermultiplets that Cyril talked about this morning, while others are genuine local operators. So, for example, the chiral operators corresponding to U1 gauge fields. So, as superconformal field theories and their extra protected superconformal representations are super rigid. There's not much that we can do to them that's interesting as superconformal field theories. So usually what we do is we study the moduli space, and we study various global properties. We keep track of masses. We study when there are points here in black where particles become massless. We study points where things become massive, and we study monodromies and all sorts of other things. Because as superconformal field theory, there's not a whole lot typically going on here on the Coulomb branch. But yeah, this is the usual picture. I ripped this off, of course, from the original Seiberg-Witten paper. And I don't think it needs to be said, but these ideas lead to enormous pseudo results and avenues that further exploration. But at the same time, in light of a lot of advances recently involving non-local operators and symmetries and topological defects, it feels like there's a much bigger playground, that gives sort of new constraints on infrared phases of theories and new relations between theories. And so, one question you might wonder is, is there more that we can do with local operators? So, of course, I should say that this picture here doesn't just assume a discussion about local operators, as Cyril nicely showed us today, right? He described various line operators and subtle differences when you study the moduli space carefully. But I'm going to sort of stick to these to local operators and ask if there are some new avenues for possible exploration. What I mean is local operators really in superconformal field theories. So there are some questions and ideas that will occupy the rest of the talk, and I'll try to give examples of all three. The first one will be a bit more experimental and will involve some conjectures that you'll see are backed up by, at least in some cases, by well-known physical results. So one question is if we can take three superconformal field theories and deform their quantum numbers in some well-defined way, so deform the quantum numbers of their protected local operators in some well-defined way, to learn constraints about all possible superconformal field theories. So here I have in mind not necessarily a picture like this, but just some sort of more abstract question, like if you start from some pre-point and you look at the spectrum, you have a set of quantum numbers. Can you deform those quantum numbers in some way that's consistent with, say, locality and unitarity to learn about constraints on all possible superconformal field theories? And we'll see that even though this might seem like a dumb idea, it works in a lot of non-trivial ways. A second point is if we can use protected multiplets to generate the local algebra of superconformal field theories, all local operators in some way. Okay. So I personally like to think of it as some kind of quantum field theory analog of Burnside's result. So Burnside has this famous result that if you take some irreducible faithful irrep of a discrete group and you take enough tensor powers, you get all possible irreps. So I have in mind something similar, like if you can take, say, all or some subset of special protected local operators and consider all, say, possible n-fold OPUs of these operators, can generate all possible operators in the theory. Of course, I'm not going to give you a proof that this is possible, but I'll give you some hint, perhaps, that I think at least is a strong hint that this is possible. Yeah. Yes. So obviously, well, I don't know if it's obvious at this stage, but the results that I'll have primarily are going to be about protected operators, but there'll be some very highly unprotected protected operators, if that makes sense. That will actually make a bit more sense later. We can discuss long multiplets if you want at the end, but yes, I mean that the idea would be to say something also about long multiplets in these OPEs. I'm not going to present to you some kind of really concrete result about that. But, so this is a second point, and yeah, maybe one sort of small point to make is that it's hard to imagine, at least for me, this kind of program in bullet 2 working without supersymmetry. So you'd have to first define what you mean by a protected operator without supersymmetry. You might mean something like a conserved current. That's a reasonable definition. But at least as far as I'm aware, outside of, say, meromorphic theories in 2 dimensions, those things don't really generate the local algebra of operators. So those would be very special examples. If you want to sort of solve this Burnside program, probably you're looking for supersymmetric theories. So the third point is that so there's been a lot of discussion about non-local operators, and one sort of dumb way to get non-local operators from local operators is of course to take a current and integrate it over some say codimension 1 hypersurface. And of course, you can also study then anomalies of symmetries by looking at contact terms of the currents and correlation functions of the currents. But you might wonder if there are more general relations between local operators and I don't know why I said non-local anomalies, between local operators and non-local symmetries and anomalies. So we'll get to that maybe at the end if there's time. So any questions? Right. So to get where I want to go, I have to introduce some kind of cast of characters. So the cast of characters are the short representations, protected representations of 4D n equals 2 superconformal field theory. And in this kind of SCFT, we have an SU2R quantum number. So this R is a weight of SU2R, this capital R. We have a U1R charge, little r, and we have left and right spins J and J bar. And for simplicity, I'm mostly going to suppress these quantum numbers below, except where they're necessary. So the first type of multiplets that we know and love are the kind that naturally arise in the Seiberg-Witten description that Cyril was describing earlier today. So these U's, these trace phi squareds are canonical examples of them. These are operators that are annihilated by all the antichiral charges of supercharges of supersymmetry. So here I is an SU2R index, goes from 1 to 2, and alpha dot is some right-moving Lorentz index, and Q bar alpha I alpha dot annihilates O. So this is what it means to sit inside this kind of a multiplet, the so-called E bar multiplet. It's just a multiplet that's chiral with respect to all of supersymmetry. So these are given by the Casimirs of the gauge group in a Lagrangian theory. And as will become crucial in this experimental part of the talk that will soon start, locality. So if you just study abstractly superconformal representations, that has no notion of locality. So that's something extra that you need to put in. And if you input locality, then you'll force, for example, the left spin of this operator O to be 0. And we'll see some other constraints that locality gives. So another set of multiplets that are important are the multiplets that parameterize the Higgs branch. So these are multiplets that are charged under SU2R, but are neutral under everything else. So they have 0 spin, 0 U1R charge, at least the primaries do. And they satisfy these chiral and antichiral shortening conditions. So they're annihilated basically by half the antichiral supercharges and half the chiral ones. Okay, so things you can think about of this type are things like hypermultiplets are canonical examples where you have R equals a half, but you can also have Noether currents where R equals 1, and you can have more general baryons in the theory. Okay, so the cast of characters is a little long there, for whatever, 5 or 6 characters. So let's get to the third one. The next guy, but I hope at least I introduced you a little bit of their different personalities so that it's not too boring. So this next multiplet this next representation is the D bar representation, and it again carries a chiral operator as its highest weight primary. So it's annihilated by Q bar 1 alpha dot, and it satisfies some additional so-called semi-shortening condition. And these typically arise when you have a mixed branch or you have extra supercurrents, as you might when you have n equals 3 or n equals 4 supersymmetry. And they're also interesting if you like class S because they do things like probe the topology pi 1 of the Riemann surface that you get in class S. And they also tell you interesting things about twist defects and other such things. And I should have mentioned, just like the B hat multiplets, they're also captured by this interesting 4D 2D map. So they can be related to some kind of chiral algebra states as well. And the special case of R equals 0, so the D bar 0 with spin 0, 0 multiplets are precisely the free vectors, the A and ADs that Cyril talked about this morning. So those are obviously very important, highly protected multiplets in the theory. So when you study those free vectors that appear in the Seiberg-Witten description, you get not only the shortening conditions in 6, but you get many more, basically by acting with SU2R lowering operators. Finally, to complete the sort of chiral sector, if you like, of 4D n equals 2 theories are the so-called B bar multiplets. I'm actually not going to dwell a lot on them. It was a subject of a recent paper from last week, but I'm not going to say too much about it. But these are sort of the most general n equals 1 chiral, the most general multiplets that contain operators that are chiral with respect to some n equals 1 subalgebra and n equals 2. So you see their primaries are annihilated by half the antichiral supersymmetries, and typically they're associated with mixed branches. So often if you take OPEs of, say, Coulomb branch and Higgs branch operators, you'll get some of these operators appearing in the normal ordered part of the OPE. So they really parameterize typically mixed branches, but there's also a much more interesting, much more general set of physical phenomena that they're associated with, which I'll touch upon maybe later. Okay, so then there are two more characters to introduce. So one additional character is the so-called C hat multiplet. So this includes the energy momentum tensor when all these quantum numbers R, J, and J bar are 0. The U1R charge is fixed in terms of the spins, and they satisfy these semi-shortening conditions I've written in equation 8. And you have additional conditions when some of these spins are non-zero. You get some first-order conditions involving contractions of Lorentz indices and supercharges. And then finally, there's a set of, so in answer to your question, there's a final set of multiplets, the so-called C-bar multiplets, which are kind of the crappiest multiplets from the perspective of short multiplets, in the sense that they are the least sort of protected. They sort of just satisfy this semi-shortening condition in equation 9. But the beautiful and interesting thing, I think, an underappreciated thing about these multiplets is that they capture really global physics about the CFT, global physics about the local operator algebra. So if you study, things like C-hat multiplets or things that are related to the Rastelli beam VOA, and you also study things related to Seiberg-Witten theory, the C-bar multiplets sort of naturally appear from the product of those two sectors. So they're very interesting. And if you want to establish some kind of Burnside-like result for SCFTs, they're nice sort of minimally protected probes for studying that question. Yeah. Yes. Yeah. 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 The pi 1, basically. Yeah. Yeah, so so there may be some very sophisticated senses in which they do. I have just a very dumb sense in mind, which is that if pi 1 is non-trivial, then these multiplets exist. But there's probably much more that you can say. I mean, they also probe some interesting things about twist defects that you can insert. Like you can. Yeah, that's right. That's right. Yeah, that's right. Yeah. For n equals 4, you always have these things because, as you know, n equals 4 has more than n equals 2 supersymmetry, so you have supercurrents. But those are. Yeah, so in the n equals 4 case, these d-bar multiplets are supercurrents, and there are, maybe some other ones, but those are kind of the most canonical, if you like, d-bar multiplets in that context. And also in n equals 3 theories, they appear as well. Yeah. I don't know if there's like a nice sort of precise statement, like, exactly. Yeah, that would be an interesting statement. I suspect that the more sort of closed, non-trivial closed loops you have, the richer the d-bar spectrum would be. But yeah, it'd be interesting to study those. Yeah. Other questions? Okay, so I want now to get to kind of an experimental part of the talk, and some will be mostly conjectures backed up by some non-trivial results. And the basic idea is going to be that free theories. I mean, we've seen this in Cyril's talk. We've seen this in Michele's talk. Free theories seem to be very closely connected with any local unitary interacting SCFT that we can construct. Usually that connection is via the RG flow, or maybe via some conformal manifold, or maybe some more exotic thing that you can do. And since that's the case, an idea would be that if in some way that I'm going to not make completely precise, but if these free theories are sort of sufficiently connected to all interacting SCFTs, then what we expect to do is to be able to take the quantum numbers, say of multiplets in the free theory, deform them in some way, and get the set of all possible quantum numbers for short multiplets in any superconformal field theory. So this may sound crazy, but we'll see that it works in very non-trivial ways. And the idea is basically, I don't know if I have an eraser here. Okay. Okay, so unfortunately, I don't know where to draw it so everyone can, I'm not sure if everyone can see, but, sorry. So I'll try to draw here. But I'm just going to draw sort of a crappy picture where, you have some free theory, say, in the IR. Maybe this is on some moduli space of the type that Cyril described. And maybe you have some interacting SCFT in the UV. And, what I'm imagining is that, any interacting theory you can find is connected through perhaps some set of flows from a free theory, okay? And when that's the case, then you can imagine somehow, well, the free theory also, of course, could be in the UV, it could flow maybe to some SCFT in the IR. But the idea is basically that if you have such continuous connections between theories, you can imagine deforming things like the U1R quantum number of the free theory in such a way that you reproduce all possible operators in interacting superconformal field theories. So, of course, you can't deform the SU2R, the spin, because these are sort of quantized. But you can imagine taking the U1R in free theories, which is a very rigid quantum number. It's basically half integer quantized, and sort of having interactions make that quantization somehow finer. So that's what happens, say, when you study flows to the Argyros-Douglas theory, where you start with some Lagrangian theory in the UV, which has half integer quantized U1R, and then you end up in the IR with some seemingly more exotic, rational quantization, finer rational quantization in the IR. Okay, so I'll explain a little bit more what I have in mind with this idea in some concrete cases. All right. Yeah, so that's the idea, basically, that interactions should somehow just change the quantization condition for U1R. Okay, so let's try to apply this idea in the dumbest possible case, but before doing that, let's just sort of figure out what the cast of characters are in free theories. So free theories for me will mean things that just consist of U1 gauge multiplets and free hypermultiplets. So U1 gauge multiplets have a primary which I'll call phi I. Phi I is some chiral operator. It's in this d bar 0, 0, 0 multiplet. So it's chiral with respect to n equals 2 supersymmetry, and it satisfies all sorts of additional shortening conditions. And it has these quantum numbers. It's uncharged under SU2R, it's charged under U1R with integer charge, and its scaling dimension is 1. Ignore this last this column delta. So E will be the scaling dimension, capital R is the SU2R weight, R is the U1R charge, and J is the left spin. And of course, it has various partners. So for example, it has gauginos, and I've picked one particular gaugino here. This gaugino is the Q1 descendant of the phi I. So I should say, runs from 1 to n if we have n free vectors. And lambda 1I, alpha, is some gaugino that's related by supersymmetry to phi I. And it has these quantum numbers. So it has some SU2R charge, some U1R charge, some spin, and some scaling dimension, which is well known from the textbooks. And then we have some hypermultiplets. So these are QA and Q tilde A. These are some scalars, the primaries of the hypermultiplets, and they have SU2R weight 1/2, and they have scaling dimension 1. And of course, there are a few extra superpartners that I've neglected here, because I'm basically just focusing on the fields inside the free vector and the hypermultiplet inside the free hyper that are chiral with respect to at least some n equals 1 subalgebra. So of course, there's also a field strength. I don't care about it. Other such things. So this idea of somehow taking, so I want to take a collection of n free vectors, so I goes from 1 to n. I want to take a collection of m, say, free hypers, so A goes from 1 to m. So the most general possible free theory that I can consider. And I now want to study the spectrum of protected multiplets in this theory, and I want to do the dumbest thing possible, which is just deform the U1R charge and see if I can land on some constraints that all superconformal field theories should obey. So in the first case, or at least all local unitary superconformal field theories. So locality is actually very important. Free fields are, of course, local, and their existence in these theories in these RG flows is very closely connected with locality. So the first example are these B hat R multiplets. So these, if you remember, are the multiplets that have the Q's as B hat 1/2. So these are sort of the Higgs branch operators. And here, things are very trivial, right? Because in a free theory of hypermultiplets, of course, you have the spin 1/2 representation. And it's pretty obvious that from taking products of these representations, you can get all possible B hat R multiplets, because you can get all possible SU2R weights. Okay, so this is not something very deep. I mean, this simple fact is probably connected with all sorts of things like non-renormalization theorems of Higgs branches, but it's kind of an obvious statement. The second example is much more non-trivial and hinges on the use of locality and the fact that free fields are local. So the next thing you can try to do is you can try to consider the epsilon bar, the E bar R multiplet. So these are the things like the Casimirs, the trace phi squareds. And at least in the context of superconformal representation theory, these chiral multiplets in principle are allowed to have left spin. Okay, so they're in principle allowed to have J j greater than 0 is allowed. But j bar equals, the right spin is 0 by the constraints of the superconformal algebra. But otherwise, in principle, this left spin is allowed to be non-zero. But you can ask, if we start from a free theory and we just deform, we imagine we have some picture where we have it connected to the interacting theories, and we imagine that the U1R charge maybe varies along that flow in some way, and all the other quantum numbers are fixed. Can we somehow see the constraint, see a constraint on these multiplets in general theories? And the answer is yes. So basically, if you study the free theories, the only possible E bar R multiplets that you can write down have spin 0. And this is because these multiplets have to be annihilated basically by all the anti-chiral supersymmetry, right, by construction. So what this means is that you can only use these primaries phi to construct them. So you can't use derivatives; those would be trivial in the chiral ring, and you also can't use lambda 1s because these are not n equals 2 chiral, right? They're Q1 descendants. So acting with one of the Q bars will give you a total derivative. So free theories predict what I have in equation 10, which is that the only multiplets of this type are ones where you have spin 0, right? And the U1R charge, as you'll notice, is also integrally quantized, but you have this 0 left spin. J bar equals 0, as I said, follows from superconformal algebra. And so the idea is that we want to relax this constraint in the way that I've described above, and then what you would predict somehow is that if these theories are sufficiently connected to all the interacting superconformal field theories, you'd predict that in any superconformal, any local, at least, superconformal field theory that you can write down, the J, the left spin of this multiple, should be 0. And indeed, you can prove that this is the case. So Andrea Manenti proved this very nicely a few years ago. So basically, it follows from locality and considering the 3-point function of the energy momentum tensor multiplet with an epsilon bar, with a chiral and anti-chiral operator, and imposing superconformal word identities. So locality of the space-time, so the existence of an energy momentum tensor, and the form of this 3-point function force you essentially to have j equals 0, which is perfectly in line with what you would predict from this idea of starting with free fields and just deforming the U1R charge. So now we can look at more complicated multiplets. So the next multiplet on the list is this D bar multiplet. So the D bar multiplet, remember, is satisfying in general some slightly more Byzantine shortening conditions than the free chiral, than the chiral multiplet. So in the case of free theories, again, you can show, it's very easy to show that for D bar multiplets, the left spin should always be less than or equal to the SU2R weight. Okay? And this just follows from the fact that the only way you can construct such multiplets is using the primary can only be constructed from operators in this table. Okay? And you can't use derivatives because the highest weight primary essentially is chiral with respect to some n equals 1 chiral subring. So, and as you see here, you know, any multiplet, any operator that you use from this table will have SU2R weight bigger than or equal to, we'll have spin greater than or equal to its SU2R weight. And moreover, if you use free hypermultiplets, then you can also decouple R from J and get any multiplet of this form, D bar R J comma 0 with J less than or equal to R. Okay. So and the reason is just that hypermultiplets, of course, have 0. Their chiral fields have 0 SU2R weight, but have non-zero SU2R weight, but 0 spin. So then if you use the same kind of logic that we've used before, this logic again suggests that more generally, in any SCFT, you should only have D bar R J comma 0 multiplets with J less than or equal to R. And so we wrote this up as partly as a conjecture with Ananya Banerjee as part of some larger study that involved less conjecture, but we wrote this up and we showed this to Andrea Manenti, who then pointed out to us that this, in fact, already follows from the average null energy condition. So what they considered is they considered 3-point functions of the energy momentum tensor with chiral and anti-chiral operators. And they considered this integrated correlator where you integrate over some null geodesic. And basically thinking in terms of n equals 1 chiral operators inside the D bar multiplet, you reach the same conclusion, essentially, that even in any local theory, any local 4D n = 2 superconformal field theory that you write down, this bound on spin versus SU2R is satisfied. Okay, so this gives some strong evidence that in some way that we would like to make precise, free theories are nicely connected, probably, with all possible local unitary SCFTs that you can write. So this also pushes us to conjecture more generalizations. So then you can start to look at more complicated multiplets. So you can take these B-bar multiplets that I mentioned before, and you can again see that they can only have U1R charge less than or equal to spin, basically because the only way to produce B-bar multiplets is to take the D-bar multiplets and sort of fuse them with E-bar multiplets, with phi fields, essentially. So you can again make this kind of conjecture here. So these D-bar multiplets are some kind of unitarity bound, and fusing with phi operators essentially takes you away from this unitarity bound. And you can again make this conjecture that B-bar multiplets in general should have spin less than or equal to the SU2R weight in a general interacting local theory. And lo and behold, what we've shown with Andrea is that indeed you can take their logic and extend it a little bit and show that this is true, at least for cases where the U1R charge is less than J plus 2. But we believe it holds more generally, and now we're working on some more sort of inherently n = 2 probes of this idea, and studying some additional observables to try to prove it for the full set of B-bar multiplets. And I should note that this is some kind of master bound, let's say, on chiral operators in 4D n = 2 theories, because it implies the D-bar and E-bar bound. So if you violated the D-bar bound, if you had D-bar multiplets with spin greater than the SU2R weight, then you could always construct B-bar multiplets violating that weight by fusing with free vectors phi. And similarly, if you had E-bar multiplets with non-trivial spin, then you could fuse with free hypers to create B-bar multiplets that violate this bound. So this is some kind of, I believe, master bound for chiral operators in 4D n = 2 theories. So this implies some severe constraint that locality puts on the superconformal algebra that goes just beyond algebraic reasoning. Okay, so you can keep going, and I will spare you all the details, but more generally, you can look at compatibility of this previous conjecture with the superconformal algebra and find that you can find additional sort of drastic truncation constraints on all possible multiplets. So for the non-chiral multiplets, the C hat and C bar, with Hong-Yang, we've constructed this additional bound, just following from consistency with the superconformal algebra. And these have various interesting applications, that I won't get to in this talk, but basically they show that there are certain new multiplets that are predicted from recombination in the index, and this will probably have all sorts of interesting applications for studying conformal manifolds and maybe RG flows. Okay, any questions about this? I'm going to switch tacts now to talk about the second point. Yeah. And the possible what? Sorry. Yeah. Yeah.
You come up with some constraints in relation to spin and asymmetry.
Yeah.
Numbers.
Yeah.
Some of them can be proven.
Yes.
Some of them are conjectures.
Yeah. But yeah, and we're working on some proofs. And the idea is just that so the idea is as basically every theory that you've probably ever written down, right? You have a flow to free fields, so somehow it's natural that taking free fields and taking sort of the sort of least finely quantized part of the spectrum, namely the U1R charge, it's somehow natural that you should be able to deform that U1R charge to sort of describe the. Absolutely. Absolutely. Yeah. So making a very precise statement in terms of the U1R charge is sometimes non-trivial, especially when you flow into the Coulomb branch, let's say. I mean, if you do other things like, flow into the Higgs branch or something like that. So in the case of the Higgs branch, you would preserve the U1R. So there are different kinds of flows you could study. Yeah, but basically like non-trivial stuff like ANEC, ward identities, all this stuff sort of point to this picture being correct. And yeah, I think we're very close to proving it for these chiral operators for the B bar. I'm less certain about the C hat and C bar. For C hat and C bar, it's more like it seems to be true. And then there are lots of interesting sort of things that you can derive from it, which we will try to use as some consistency checks. So for example, there are these multiplets that are protected from recombination. So you end up with some predictions possibly for the index in various theories. So these are sort of avenues that we're looking at. Okay, so the next thing I wanted to talk about is this idea of whether you can use somehow the protected multiplets to say something about the full spectrum of local operators. So obviously this is kind of a very ambitious thing to do. So somehow you want to be a little less ambitious, at least at first, and you at least would like to limit yourself to maybe a particular theory, a particularly nice theory. For free theories, this statement is kind of trivial because you can just construct words out of free fields, and there's nothing really to study. It's only interesting for interacting theories, this question. So if you study interacting theories and you want to understand if the protected local operators can generate the algebra, then obviously you want to try to study the simplest possible examples, where simple may be a matter of taste. But at least for me, the simplest example of a 4D interacting n equals 2 theory is the so-called original Argyros-Douglas theory, or as I'll just call it, the MAD theory, the minimal Argyros-Douglas theory. So this is a theory which, unlike a gauge theory, which has matrix degrees of freedom, basically has some reduced number of degrees of freedom because it lives on a Coulomb branch, essentially, of some gauge theory. So I'm going to dwell a little bit on why this theory is simple, in order to, in the process, explain to you why it might be possible for protected operators in this theory to generate the local operator algebra. So dwelling on the simplicity, one way to see it is what I just said, which is that this minimal Argyros-Douglas theory arises on the Coulomb branch of some UV gauge theory. And so it has fewer massless degrees of freedom because you've Higgsed a bunch of crap. So the MAD theory, for example, can be engineered from two of the simplest n equals 2 gauge theories. So one is SU3 n equals 2 super Yang-Mills, which was the original theory Argyros and Douglas studied, or from SU2 with one flavor, n equals 2 super QCD, with which Argyros and a bunch of heavyweights from IAS studied the year after. And roughly speaking, here's my crappy diagram. I mean, it's very bad for what happens, but you have some Coulomb branch here. And, you have some point where, I don't know, I've drawn two lines going to that point. I'm not exactly sure why, but you go to this point and sort of mutually non-local massless particles exist at that point. So you have this BPS quiver where you have sort of two mutually non-local particles charged under, the electric and magnetic U1s becoming massless at this point. So this minimal Argyros-Douglas theory itself is rank 1, it turns out, and this sort of non-locality of things, these non-local charges that become massless at the same point, result in some kind of, singular curve. And from that singularity, you can read off that this chiral operator that I've discussed, this epsilon bar, there's an epsilon bar generator, which has U1R charge 6/5, so it has this sort of more exotic quantization compared to a free theory. The sort of poor man's way to understand this theory is as some kind of basically U1 fixed point, where you have basically two charged hypers that are sort of charged under the electric and magnetic U1s. And as you know, in 4 dimensions, if you had only electrically charged particles, you'd get an IR-free theory. So that's what happened in the example that Cyril talked about this morning. But more generally, you could study theories that have some mutually non-local electric and magnetic charges that become massless at the same point, and then you can imagine some non-trivial fixed point. And at the Argyros-Douglas point, you have two multiplets where this happens, two multiplets that become massless, and so this is sort of the simplest, at least from the effective field theory point of view, sort of the simplest possible interacting fixed point that you can imagine in 4 dimensions. Basically, a U1 theory with two massless hypers. But this is kind of an effective field theory explanation, and so this is a bit more complicated than that, and so it would be interesting to say something about the simplicity and then about this possibility to generate the local operator algebra just using arguments at the SCFT point. So one way to understand the simplicity from the point of view of superconformal field theory is to take a subset of the operators that I've described in the cast of characters earlier on, basically focus on what are called the Schur operators. So these include the C hat multiplets, so things like the energy momentum tensor. They include the B hat multiplets, so things that parameterize the Higgs branch, and these D and D bar multiplets that include sometimes extra supercurrents or various other possible operators. And then using some results on BPS state counting due to Cordova-Shao, combined with this 4D-2D correspondence I alluded to by Beam and Rostelli, it's possible, it's not too hard to argue that, in fact, and this is what we did in a paper from a while ago, that the only possible Schur operators in this theory are essentially just operators of the form C hat R, JJ. So they are just essentially bosons of C hat type. So it's kind of obvious there's no Higgs branch. Maybe it's a little less obvious that there are no D and D bar multiplets, but this is something you can more or less prove starting from the results of these people here. So to understand the simplicity at the level of the Schur sector, well, first of all, obviously, most of the possible Schur multiplets are absent in this case, so this looks very simple. But you can also study the Macdonald index of this theory, and studying the Macdonald index essentially amounts to counting operators in, particular operators in these Schur multiplets. And since all the Schur multiplets in this case are bosonic, the index is really some nice thing in this case and doesn't involve cancellations between bosons and fermions. And so you can really learn something about the space of Schur operators in this case. And using some interesting sort of analogies with statistical physics, Foda and Zhu sort of found this nice sort of closed form for the superconformal index, which looks extremely simple in equation 17. And what it turns out is using some nice results that I won't really have time to describe on arc spaces, you can essentially prove that this partition function arises from a four-dimensional theory where basically the only generator of the Schur multiplets is the energy momentum tensor, in particular the Schur operator inside the energy momentum tensor, where it satisfies some kind of nilpotency condition. So this J11 plus dot is the Schur operator. It's some SU2R current sitting inside the energy momentum tensor multiplet, and it squares to zero as an operator. This is an exact statement. It's not a statement about zero in some protected ring. It's a statement zero literally on the nose as an operator. And using this fact, you can just reproduce this partition function in 4 dimensions. So another indication of the simplicity, and soon I'm going to come back to what this means for the generation of the possible generation of the operator algebra from short multiplets. But another indication of the simplicity is that basically the entire Schur sector of this minimal Argyros-Douglas theory is in one-to-one correspondence with some subsector of the Schur operators you can build out of free vectors. So in particular, yeah. This was the Macdonald index. Yeah, so it counts the same operators as the Schur index, but with a refinement. The nice thing is that this four-dimensional line of reasoning in equation 19 gives you not just the Schur index, but the Macdonald index as well. So, this is the SU2R current, so it has this is the highest component of the SU2R current, so it has SU2R weight 1, so it makes some particular contribution here. And basically all the possible operators that you can construct in 4D that contribute to this partition function to any order are essentially normal ordered products of this and derivatives, essentially. So this gives you slightly more quantum numbers than the Schur sector, but it counts the same operators, but in a more refined sense. Yeah. Good question. Yeah. So right. So I think yeah, this is a somewhat unorthodox limit. Let me think for a second. Yeah. In this case, it's taking t to 1. Yeah. This is not the usual way that you would write the Macdonald index, but it's equivalent. Yeah. So there's some whole nice story here, basically about showing this in 4 dimensions. It's extremely mathematical, and I won't get to it. But yeah, a basic point is that these operators in this theory, in some sense, it's even simpler than the free vector. So basically, you have a single generator in this Schur sector. It's this SU2R raising current, and if you sort of follow it along the RG flow to the Coulomb branch, then this has to flow basically to the SU2R current of the free theory, which is just built from the gauge nodes. These are the only things that are charged on the Coulomb branch of the minimal Argyros-Douglas theory under SU2R. And you can also argue, basically in this case, that there's no mixing. So more generally, you can take any sort of monomial or polynomial that you can write involving this four-dimensional operator and relate it to a special set of Schur operators in the infrared theory. So in this sense, it's an extremely simple theory. It's simpler even than the free vector. Of course, it doesn't have all the representations that a free theory has. It doesn't have the higher spin currents that you'd have in a free theory. So it really contains almost like, in some bizarre sense, it almost contains sort of a subset, if you like, of the operators of the free vector. Of course, this is a bit too simple because we're just looking at the Schur sector. If you look at other sectors, there are some operators that decouple along the flow. But at least for the Schur sector, you see that this theory is basically even simpler in some ways than the free vector. So it's an ideal case. It's an ideal theory to try to look at for questions of, understanding the operator algebra of the theory. So we've seen that sort of J generates the Schur sector, but we'd like to say a little bit more, ideally also about long multiplets. As I said, we'll sort of obliquely get to that. We have some vague predictions for long multiplets as well, but I'm not sure I want to make those public yet. So basically, so what we want to do is we want to look at which operators might possibly generate the local operator algebra. And so the idea is that we've seen that this theory is very closely related to the free vector, right? I mean, basically, in the poor man's version of the theory, you essentially have a U1 fixed point with two massless hypermultiplets, and you get some U1 fixed point. So it's very closely related to the free theory. And the free theory itself, at least at generic points on the Coulomb branch, just involves basically these operators that appear in the Seiberg-Witten description, these A's, and the U's and these types of things. And so the natural guess would be that to generate the local operator algebra in this theory, you should consider repeated OPEs of chiral and antichiral operators. This would be the kind of guess that you would make. Of course, the first thing that you would want to understand is which chiral and which antichiral operators. So as I've introduced earlier in the cast of characters, right, we have, when you talk about chiral, it's a bit ambiguous because basically all these representations here, oh my God, I've gone too far. All these representations here, epsilon bar, b hat, d bar, b bar, these are all in principle chiral. D bar is not present. I've argued b hat is also not present, but you could also worry about the b bar. And I'm not going to dwell on those multiplets, but suffice it to say, you can essentially take an n equals 1 Lagrangian for the theory. So even though it doesn't have an n equals 2 Lagrangian, the Argyros-Douglas theory is known to come from an n equals 1 theory, which sort of accidentally enhances to n equals 2 in the IR. And using that Lagrangian, you can essentially argue that basically the only possible chiral ring generator that you have in the theory is epsilon bar 6/5. So the natural conjecture then would be that all local operators in this theory are generated basically by repeated OPEs of epsilon bar and epsilon. So epsilon is the antichiral operator with r equals -6/5. So one sanity check of this conjecture, which is already, I think, non-trivial, is that if you take epsilon bar 6/5 and epsilon -6/5, you are forced by word identities to include the energy momentum tensor on the right-hand side. This is non-vanishing OPE coefficient. And so the fact that we showed earlier that this C hat 0, 0, 0 generates the entire Schur sector is, of course, then compatible with this conjecture in a non-trivial way, right? It could have been that you had a bunch of other C hat multiplets that were some random crap that wasn't related to the energy momentum tensor that didn't appear necessarily in these OPEs, but that's not what happens. So to get some even stronger evidence for this conjecture, what I would like to do is basically study the least protected multiplets, these C bar multiplets that I mentioned earlier, and sort of see if we can see some kind of imprint of these OPEs on this part of the spectrum. So these are kind of the closest thing that one can get to long multiplets without really going to long multiplets. So, and they're mostly ignored in the literature, but they're quite interesting, I think, as you'll see, I hope. So in particular, well, we've studied by now already in a couple of papers a more general set of multiplets, but just for the purposes of this discussion, I'll focus on a particular set of slightly simpler C-bar multiplets. So these are ones where you set SU2R weight to 0 and you set the right spin to 0. And we want to study the exact spectrum of these multiplets in the theory. And it turns out that you can actually study the exact spectrum, and these have some very nice interpretation in terms of these generation conjectures. So the reason that these C-bar multiplets in particular, these C-bar 0, R, J, 0 multiplets are interesting is that basically through the use of the n equals 1 Lagrangian, we killed off the B-bar multiplets. We already knew there were no B-hat multiplets. There's no Higgs branch. That's kind of trivial and obvious. There's no D-bar or D operators. Again, this can be argued. I'm not going to get into the details, but it can be made essentially almost Bourbaki level, as close as you can maybe in this subject. So basically what you're left with is C-bar multiplets, and then it's just the fact that these C-bar multiplets that I'm highlighting here are completely free from ambiguities in the index. So you can, in principle, if you're strong enough, you pick a nice change of variables, you can study them exactly, and that's what we did, and we found the spectrum of these multiplets for all possible quantum numbers R and J. And you can interpret them, so you have basically if R takes this form here, then, J has to be 0 or 1, and this is the number of operators with quantum U1R quantum numbers R and SU2 left spin J, and it takes this pattern here, right? So this U1R quantization, you see this 6/5 n plus J over 5. So this 6/5, as you might imagine, is intimately connected with this Seiberg-Witten epsilon bar 6/5 operator. In particular, you can show that these two families of multiplets, basically what they come from is OPEs, essentially, well, M here should be thought of as a chiral primary, the dimension 6/5 operator, the Argyros-Douglas theory. They can be gotten from repeated OPEs, basically normal ordered products of the chiral operators of dimension 6/5, n of them, with the energy momentum tensor primary. So this gives one set of these multiplets, one infinite set for all n. And the other one comes from basically these kinds of normal ordered products of the OPE of chiral operators with themselves. Okay? And these channels, these OPE production channels, saturate this spectrum, essentially. So what you learn effectively is that basically all these multiplets here that you construct, this exact result essentially is reproduced, of course, from these types of OPEs, from OPEs involving epsilon and epsilon bar, with arbitrarily many epsilon or epsilon bar. So it's quite interesting because you see you get some universal set of multiplets, exactly the same operators turn out to be present on the Coulomb branch, and there's a way to argue this using some kind of spurion analysis. In fact, all the multiplets, the fact that all these multiplets can be explained through the OPEs that I described, and the fact that these multiplets are sort of the least protected short multiplets that you can write down, suggests at least that, combined with the fact that the Schur sector is just generated by this C hat 0 multiplet, suggests, I think, at least to me, fairly convincingly that this conjecture is probably true. Okay, so that's the last bit of that. I can now move on to my third point, if there are no questions about that. Okay, so the last topic I'm going to discuss is the question of, are there any new kinds of relations that you can come up with between local operators and symmetries? So as I mentioned, as everybody knows, since their first classes in quantum field theory, the most obvious way that local operators are related to symmetries is through Noether currents and integration over some codimension 1 surface. In supersymmetric theories, not particularly more insightful statement is that, of course, all the superpartners of the currents are also obviously present when you have a symmetry. And you might wonder, what about more general protected local operators? Like if I give you some set of symmetries that a theory could have, can you tell me what kind of representations you expect to be present? Okay. So one sort of the first place where you might try to answer this question is in theories with the maximal amount, or at least more than n equals 2 supersymmetry. And there, of course, when you have more than n equals 2 supersymmetry, as we discussed with Michele a few minutes ago, there's this d bar 1/2 multiplet, which contains the extra supercurrents. But there are also, in general, other multiplets that you can show are present. So although I'm not going to have time to tell you about the details, essentially using locality and unitarity, you can argue, for example, that the normal ordered product of these supercurrent multiplets, that it's non-vanishing, and it gives you some non-trivial B-bar multiplet, for example. So in any theory with n greater than to 2 supersymmetry, not only do you have supercurrent multiplets present, for example, but you have some canonical B-bar multiplets present. And you can try to sort of work this up in orders, in powers of d-bar 1/2, and it looks interesting because it looks like it leads to some kind of infinite ring, and possibly some algebraic proof, maybe, at some point, not right now, but at least it hints towards some algebraic proof of the existence of some kind of mixed branch in theories with n greater than 2 supersymmetry. So Michele was earlier mentioning in his talk this crystallographic, this idea that n equals 3 theories are related to crystallographic groups. So that's an idea where you essentially, in some sense, take the vacua, the existence of vacua, like moduli spaces, for granted. Here, the idea is that you would just start algebraically, or try to start algebraically, just from a set of consistency conditions, namely locality and unitarity, and at least try to bootstrap an infinite ring. Okay, and when you have an infinite ring, at least that might be the first step in some algebraic statement that a moduli space really exists. Okay, so what about relations with anomalies? Again, we know when you have currents, you have usual ABJ type anomalies. You look at contact terms of correlation functions of currents, but you can ask if other types of operators can detect anomalies besides currents and besides contact terms and correlation functions. And so one sort of place where I have been thinking for quite a few years and tried to think about a few years ago with a former PhD student and was kind of disappointed not to be able to do it, but somehow I couldn't get, I was curious to study this Witten anomaly. So you know that if your theory has SPN global symmetry, you know that the fact that pi4 of SPN is Z2 essentially gives you some kind of anomaly that you sort of diagnose by performing large background gauge transformations under SPN. So this was the Witten anomaly. So you as long as you don't gauge that SPN, of course, which you're really not allowed to do, this is some kind of 't Hooft anomaly. And you can try to ask, like, will there be additional local operators present when a theory has a 't Hooft anomaly, at least when you have n equals to 2 supersymmetry? And the answer turns out to be yes. And this sort of uses sort of a very nice result, recent result, I guess, from the last 5 years of Iñaki and collaborators, where basically they argue that a TQFT can't saturate such an anomaly. And so what that means is that, if you have some flow where you preserve an SPN global symmetry, then you need some massless degrees of freedom that are charged under the SPN. So what kind of flows will produce that? Well, a very simple example would be n equals 4, SU2, n equals 4 theory. That has one of these anomalies for SP1, basically because you have 3 hypers, so you have 3 doublets. And if you turn on an expectation value for the trace phi squared in n equals 4, SU2, you go down to U1, n equals 4, and you get a single doublet of SP1 in the IR, so the anomalies match. And this is a consequence of a much broader theorem, which you can just prove. It's just an abstract algebraic fact that Coulomb branch operators, so these epsilon bar operators that I mentioned, that they are uncharged under flavor symmetries. This just follows from basically analyzing the OPEs of epsilon bar times epsilon. So since Coulomb branch operators are uncharged under flavor symmetries, anytime you turn on an expectation value for the primaries, you get a flow, an RG flow that respects the SPN symmetry. And so whatever happens in the infrared, you have to get some massless degrees of freedom that saturate the anomaly. So in particular, what that means is that there has to be some moment map mu in any such flow. So in the case of n equals 4 super Yang-Mills, it's a bilinear in the infrared U1 n equals 4 fields. But more generally, it's some abstract mu multiplied by some Coulomb branch phi squared of the type that Cyril mentioned earlier in the talk earlier. And you can construct this normal ordered product in the IR, and you get this V bar multiplet. And then, at least if you believe the lore that mixed branches that mixed branches should involve a B-bar multiplet, then you have such an operator in UV. Also, sort of maybe, I think more rigorously, you can argue using sporions, and this is what we did, one of the things we did in this paper, that basically once you start with such a multiplet on the Coulomb branch, you have such a multiplet as well in the UV. So basically, anytime you have this Witten anomaly, one way to diagnose it is basically through some adjoint valued, essentially. So this B bar multiple, of course, will be adjoint valued because this current transforms in the adjoint of SPN. So one way to diagnose this 't Hooft anomaly through local operators is essentially looking for adjoint valued B bar multiplets of this type. So okay, so conclusion. So the hour's up. Yeah, obviously it would be nice to prove these conjectures. And also probably an interesting thing would be to try to tie the existence of protected local operators to additional structures of current interest. So things like two groups, let's say in more general structures, we've seen that they already know something in supersymmetry about the Witten anomaly, which maybe is somewhat surprising because, well, the Witten anomaly doesn't seem to have much to do with local physics. So it would be interesting to try to understand if there are relations with other sort of non-local structures that people are actively considering these days. So yeah, so we'll see. So thank you.
Maybe I have just a curiosity. Do you foresee this method can be helpful? I mean, for non-Lagrangian theories, maybe you can extract some indices which do not capture, I mean, not the full index. Do you think that listing these multiplets, you can reconstruct the index? I mean, maybe you know the Schur index of some non-Lagrangian theory. With this extra information, do you think you can reconstruct the entire index?
Yeah, it's possible. So one thing, yeah, yeah, there are definitely a lot of things that one can say about the index. So one thing that you can say, I think, is that there are definitely new slices of the index that you can construct, I think. So that's something that we're also looking at, some sort of standard slices of the index. And from that, I suspect that you will get some additional information.
So there's a notion of, I mean, these slices, I think is very interesting.
Yeah. Yeah. I mean, there are definitely some new, using information that I've given on these slides, it is possible, I believe, to construct some kind of new slices, so some new limits, if you like, of the index.
It looks that those indices are, of course, we know that are less sensitive, but especially for being non-Lagrangian theories, and I mean, there are some subtleties that emerged. And I think it would be nice to have something better than this.
Yeah.
Blind to some features that are actually important to get theories apart.
Yeah, definitely. Yeah.
Any more questions? Okay.
So one question was, for this next formula for the McDonald index.
Yeah.
For the does it have an higher origin, like the Schur index?
Yeah, for sure. So this is something. So we have a recent paper with. Let's see. So let me try to go back to this slide. I think this. Yeah. Right. So the answer is yes. So this is something that we had a paper, I think, at the beginning of June, if I remember correctly, with Hong Yang and Shimaya. And basically what we do is we essentially compute this index to all orders, like an exact computation, just using gauginos. So you know the standard result, the old result of Cordova and Shao was basically they could compute the Schur index, not the McDonald index. They did it through essentially looking at massless and massive BPS states, and they had some clever, very nice counting formula. So here we kind of are completely agnostic and working orthogonally to that. We're just basically keeping track of operators along the RG flow. There's not much to keep track of because basically there's one operator that generates the entire Schur ring. So this can be shown essentially. And this is the SU2R current. We just follow the SU2R current. And then we construct expressions for products of the SU2R current in terms of, products of lambda bar, essentially, and count those. And you can count them completely explicitly, like really a mathematical proof. And you get this formula on the nose in the infrared. Yeah, that's a good question. So in the same paper, we essentially give a proof for all the A1, A2, N theories. I suspect, I believe that for some theories, it's not enough to just look at the Coulomb branch. So the simplest example that I'm aware of, so you probably also know from Cordova and Shao, they studied these AN, AM theories more generally with, arbitrarily complicated N and M. And I think if you study something like A2, A3, for example, just to give a very concrete example, this is some W3 minimal model, I think, the Schur sector. And what you can basically show is that there's no way to construct just from gauginos alone and derivatives. There's no way. So in other words, from massless fields on the Coulomb branch, there's no way to construct the corresponding current.
I think, the A1, A2,
Yeah,
those are examples of theories that don't have an instance.
that's right.
That somehow, like in the geometric engineering picture, let's associate the fact that those are terminal singularities.
Mm-hmm.
You don't have a Calabi-Yau resolution, so they don't have deformations.
Mm-hmm.
Maybe there are other terminal singularities in the more general Douglas type thesis
Mm-hmm.
that can have the same type of.
Interesting. Yeah. That's
a Higgs branch, then probably the same technology.
Yeah. I mean, my feeling is that basically you need a couple things. So first, saying you need is probably too strong, but at least what seems to be the case is that, so you have some hidden symmetry basically coming from this VOA, like hidden in the sense that, it's not manifest, like you have to do this twisting procedure or something comparable in order to see it. And somehow you would want that thing to correspond to some genuine symmetry maybe of the theory. So in the case of the Argyris-Douglas theories, A1, A2n, it does. You have the Virasoro symmetry, which is the hidden symmetry, and it corresponds to the SU2R essentially, right? Because basically this energy momentum tensor, under Rastelli's map, this becomes essentially the holomorphic energy momentum tensor. In 4D, it's just the generator of the SU2R. So there, of course, when you flow to the Coulomb branch, basically SU2R is preserved. You don't break it because you just turn on an expectation value for something SU2R neutral. And moreover, it doesn't decouple, right? So I feel, although I don't have proof, but I feel at least that you would want something like that where you have a bunch of symmetries that are unbroken and don't decouple in some way. Maybe that's too strong, but so I suspect it doesn't work in general. So for example, for A1, theories with a Higgs branch, A1, A3, right? That has a Higgs branch. Obviously, if you go to the Coulomb branch, you give mass to all the, Higgs branch crap. So you will never recover an affine algebra by looking at the Coulomb branch. So that's an example where, of course, the symmetry is again unbroken because the VAV of the Coulomb branch operator is uncharged under it, but the symmetry decouples. So you would want, I think, symmetries that are unbroken and non-decoupling. But I believe that there's like a much more general set of theories where this should work, and maybe geometric engineering shed some light on it. Yeah, that'd be interesting.
More questions?
Thanks.